The broadcast is now starting. All attendees are in listen-only mode.
Hello everyone, I would like to start this webinar session. I am Hideyuki Terashima from the University of Illinois and will be moderating this month's Joint Centers webinar. This webinar provides an opportunity for Centers students to present about their research. We will have 3 presentations this session. Each presentation will be given 50 minutes and will be followed by a 5-minute Q&A session. Please feel free to ask questions anytime using the chat box feature on the GoToWebinar app. This webinar will also be recorded and posted on the drinkingwatercenters.net website after this session. Our 3 presenters today are Darlene Balin from University of New Hampshire, Ki Yale from University of Texas, and Rachel Marshall from University of Guelph. Currently, Darlene isn't connected to the GoToWebinar app, so I'm not sure if she's connected to or if she's listed under the attendees, but for now we'll start off with our 2 presenters that are currently here. So at this moment, I will be changing presenters to Ki. Feel free to start whenever.
Okay, so hello everyone, this is Ki Yale from UT Austin. Today I'm representing Wind Center. So the title of today's talk is Interrelationship of Inorganic and Organic Contaminants and its impact on metal-based precipitates. So basically it will be about how these different types of contaminants can interact during coagulation process, and also how the contaminants can affect on the precipitations. So this is a simplified description of coagulation process. The raw water containing various different types of inorganic and organic contaminants comes into the water treatment process, and ferric chloride and aluminum sulfate are most commonly used as a coagulant to get rid of those contaminants.
Sorry,
so
Ki.
Today's
If you don't mind pausing you for a second, your screen on our end is kind of zoomed in, so I'm not sure if you can zoom out of your screen or if you're on the we're seeing like a corner of your screen.
Okay.
So try going into presenter mode again. Yeah, it's still zoomed in. I'm not sure if it's showing the slides or like actually, why don't you just present it not in presenter mode, just so we can see the whole slide.
All right.
Yeah.
Oops. Would this work better?
Yeah, that should be fine.
Okay. So again, so today's presentation is closely related to this box area, coagulations, and flocculations. Oops, sorry. So we do have 2 objectives. The first objective is to understand this interrelationship between organic and inorganic contaminants. And we use the extracted natural organic matter from Lake Austin, and also use the different types of inorganic substances, fluoride, arsenic, and chromium. Ferric chloride and aluminum sulfate were used as a coagulant, and pH was targeted at 6.5, and otherwise it is noted. And the second objective is to identify the flow characteristics of these iron and aluminum precipitates. So we use XPS to see how the chemical composition is changed in different conditions, and also use the Cota counter to measure the physical size and volume change. Oops. So before we move on to the data analysis, here's how we interpret particle distribution measurements. So the x-axis is log of particle diameter, and y-axis is volume distributions. So the area under the curve is a particle volume concentration, and the peak diameter is where the highest volume distribution is. So first, let's look at fluoride in alum coagulations. So on top left, particle distribution curve indicates presence of fluoride decrease both peak diameter and particle volume, as 50% of fluoride is removed during this test. And the illustrate on the top right shows the interaction mechanism. So fluoride can incorporate into the aluminum hydroxide precipitations by replacing OH- ion, which has the same negative charge, and that leads to the inhibitions of the further aggregation. And this is also supported by the XPS data, showing that the decreasing aluminum to oxygen ratio is increasing aluminum to fluoride ratio in the presence of fluoride. So next is natural organic matter in alum coagulations. So unlike fluoride, presence of natural organic matter actually increased the peak diameter and the particle volume, as NAM was removed approximately like 35%. So I think there are two possible interaction mechanisms. First, a large and also the complex natural organic matter molecules can absorb onto the aluminum hydroxide surface. And second, NAM itself can breach the precipitates, which results in forming a larger flux. And these are the hypotheses, so definitely more research is needed. Then what will happen if both fluoride and natural organic matter are presented at the same time? So in a particle size distribution plot, green colored triangle curve indicates dual ligand system, both natural organic matter and fluoride at the same time. You can see it shows an intermediate trend of the single ligand conditions. So the remover % data in the table shows the decreasing trend for both fluoride and natural organic matter, and that's just a competitive interactions between fluoride and natural organic matter. Then how about fluoride in ion chloride coagulations? So blue colored square is ferric chloride with fluoride. So if you compare blue square to the black circles, which is the no ligand, so FeCl3 alone, you'd see a shift of a curve toward a smaller diameter in presence of fluoride after 30-minute mixing. Since fluoride is barely removed in ion coagulation, we could infer that fluoride interferes or delays the aggregations of iron hydroxide. So we increase the mixing time until 90 minutes, and it is appeared as red square in a particle distribution measurement. Oops. Sorry. As you can see, the volume of smaller diameter is decreased as larger diameter volume is increased. And this indicates that somehow the delayed aggregation due to the fluoride presence recovers as increase in mixing time. So in other words, increased mixing times allows the aggregation of the flux. So one thing that I want to briefly mention before moving on is that I also observed some big size flux during this measurements, but I think I probably missed those big size flux during the measurements since it is settled too fast while I sample out. So I'm trying to resolve this problem at this point. So here's the results when fluoride and NAM are co-presented in ion coagulation. So when NAM is a single contaminant in the system, which is shown in black cross in the plot, the volume and peak diameter are increased tremendously. However, when both fluoride and NAM are present, the inhibition effect of fluoride is dominated, and it results in a smaller peak diameter and a smaller volume as well. And this is also revealed in remover percent data that a presence of fluoride actually decreased the non-remover efficiency. And this is that natural organic matter is more impacted by the presence of fluoride in competitive way than vice versa. So there are two possible reactions in this system. First, fluoride is interrupting natural organic matter and Fe interactions, and it decreased the flux size and volume, as well as it decreased the remover efficiency. And even if it's minor reactions, fluoride still can form the soluble non-fluoride complexes. So we could also see a similar, some sort of recovery trend as we increase the mixing time until 90 minutes. So after 90 minutes, it is appeared at red triangles in a particle size distribution plot. And flock diameter approaches the similar number in diameter as the case of in the absence of fluoride, and so does volume. So let's switch to the different inorganic contaminants, arsenic-3. The presence of arsenic-3 hardly changed the physical flock characteristics in alum coagulations, as you can see in the particle size distribution plot. So this is consistent with remover percent data showing only a small amount of arsenic-3 is removed, under 5%. So we could say that arsenic-3 presented as an oxyanion has only small impact on the aluminum precipitation. And here's the result of arsenic-3 and natural organic matter. So particle distribution plot shows only small change in presence of arsenic-3, both in single and dual ligand conditions. So the remover data in the table shows the interesting results related to this trend. So non-remover was barely impacted by arsenic-3 presence, while arsenic-3 remover actually increased in the presence of natural organic matter, which is indicating a synergistic interactions. So this could be explained with the illustrates on the top right. So arsenic-3, the oxyanion, still can directly bind to the aluminum hydroxide, but the arsenic-3 forms natural organic matter and arsenic-3 complexes, and they can be removed by this aluminum precipitates. And the synergistic interactions must be the dominant reaction mechanism here. And there's a quite different trend shown in ion coagulation. So again, arsenic-3 presence shifted curve toward a smaller diameter range. So based on the fact that arsenic-3 remover is reached up approximately 48%, what could be happening is that oxyanion of arsenic-3 can directly bind to iron hydroxide, and it retards the nucleations or the further aggregations of iron hydroxides. And the huge increase of iron to oxygen ratio in XPS data in the presence of arsenic-3 also proved the decrease of block size, which leads to the lower iron content. When both arsenic-3 and natural organic matter were present in the ion coagulation, the effect of arsenic-3 is more explicit. So both contaminant remover were decreased in dual ligand system, and that indicates competitive interactions of arsenic-3 and NAM. And also, if you look at the illustrated on the top right, the competitions of oxyanion, natural organic matter, and arsenic organic matter complexes is also correlated to decrease of block size and volume. So for chromium, today I'm going to present preliminary test results only. So here's the chromium 3 and 6 in alum coagulation. So left plot shows a chromium remover in different pH condition, And both chromium 3 and 6 shows synergistic interactions with natural organic matter. So chromium 3 remover is enhanced by natural organic matter, particularly a lower pH, 4 to 5, while chromium 6 remover is higher in most pH range in the presence of NAM. And on the top right, residual aluminum plot is consistent with the results from the literature that's typically U-shaped curve, and it has the low solubility in neutral pH range. And one thing is at lower end, particularly at pH 4.5 to 5, and also the higher end at pH 8.5 to 9, we observe that natural organic matter presence also slightly decreased the aluminum solubility. And chromium in ion coagulation showed a little bit different trend. Chromium 3 showed a synergistic remover in presence of natural organic matter, particularly a lower pH, again 4 to 4.5, just like in alum coagulation. However, chromium 6 showed competitive interaction with natural organic matter in most of pH range. So it decreased the remover percent in the presence of natural organic matter. And the interesting part in ion residual plots in a right side, particularly the boxed area at acidic pH range, presence of natural organic matter actually induced lower solubility of iron, which is the increased ion precipitation rates. And for this particular part relating to NAM effects on accelerating ion precipitation rate, more research is actually ongoing right now. So here's the conclusion of today's talk. Different types of inorganic contaminants can interact in different way with NAM. So for example, fluoride shows competitive interaction to NAM in both alum and ferric chloride coagulations. And arsenic 3 and chromium 6 showed a synergistic interactions in alum coagulation, but the competitive interactions in ferric chloride coagulations. And for chromium 3, it showed both competitive and a synergistic interaction to NAM in alum and ferric chloride coagulations. And also the presence of anions, oxyanions, natural organic matter, or the combination of them can affect the precipitate morphology in different mechanisms. So that's all for today's talk, and I'm happy to take any questions. Thank you.
Well, thank you, Ki. At this point, we'll like to move on to our Q&A session. So far, we have one question. What exactly was your laboratory setup you used for your analysis?
So I used a jar. I'm not sure if you were familiar with the jar test. Basically, to measure the remover efficiency, we do use the jar test procedure.
Mm-hmm.
So it's 30-minute mixing, use different types of coagulant and different combinations of contaminants.
And then you take the sample and put it under, or go through XPS and just look at the particle size. Is that simply?
Yeah.
Okay.
Yes.
Cool. Great. All right. Well, again, if anyone has more questions for Ki, just again ask them using the question tool, and we can get back to those questions. So Ki, at this point, why don't you change presenter to Rachel?
Okay.
Rachel, you should be able to show your screen to everyone, and you can start whenever you're ready.
All right. Hello, everyone. So I'm Rachel Marshall. I'm a PhD candidate in water resources engineering at the University of Guelph. And today I'm going to be talking to you about a source water protection project that is a collaboration between the Chippewas of Nawash Unceded First Nation and the School of Engineering at the University of Guelph. So I'll start by discussing the purpose and giving you an intro to the project, and then I'll talk a little bit about the groundwater studies we've completed so far and the community engagement and Indigenous knowledge aspects of the project, and then I'll discuss our upcoming work. So the project began in 2014, and I was invited to join the process by a band counselor at that time to do some hydrogeological studies on reserve as part of their source water protection plan that they were hoping to launch. And we were also interested in finding out how the process of source water protection could be improved for First Nations. Basically, right now, the on-reserve guidelines essentially suggest bypassing hydrogeological studies due to cost, and they suggest using rules of thumb to determine wellhead protection areas, for example. And this is particularly problematic for First Nations that are located above vulnerable fractured rock aquifers like Nawash. So a water protection committee was struck in the community, and currently it consists of elders, community members, and band counselors. So the overall purpose is to support the development of effective First Nations source water protection plans that are informed both by the technical knowledge but also by Indigenous knowledge. And specifically at Nawash, we're aiming to develop a source water protection process that works for the Chippewas of Nawash and which could also be shared with other First Nations in the future. So the project has two components. There's groundwater studies to provide the band with technical information so they can make decisions. So that's included sampling, conducting tracer experiments, and modeling. And the second component is a community engagement piece to make sure that Indigenous knowledge and the community's priorities are at the foundation of the plan. So we're bringing these two elements together to build a framework that will work for the community. The Chippewas and Nawash are located on the south end of the Bruce Peninsula near Wyerton, Ontario. And the field site where we've been conducting our groundwater studies is located near the boundary of the reserve. So the white dots represent our CMT multi-levels, and the squares indicate septic systems. So we're essentially aiming to determine whether or not the septic systems are impacting the wells. So the primary concerns for the community include impacts to vulnerable areas and important wildlife habitats from septic waste, dumps, storage tanks, and abandoned wells. So in terms of the fieldwork that we've completed to date, we've retrofitted 3 unused drinking water wells into multi-level monitoring systems called CMTs. And for those of you who aren't familiar with them, CMTs, they essentially look like wagon wheel pasta, and they have 7 ports installed at different depths. So essentially it's like having 7 wells in one. So we conducted a number of tests on the open wells before installing the CMTs, and we sampled them monthly from July 2015 to November 2016. And we also sampled a few other locations around the reserve and conducted some tracer studies with an organic dye and also 3 artificial sweeteners. So here we are doing some pumping tests to see how much water these wells produce and collecting some field parameters in the open hole before installing the CMTs. We also ran some geophysical surveys. So basically we lowered a number of instruments down the well to take measurements and snapshots of the borehole wall. And this gave us an idea of where the major fractures that produce water might be located, which was important for designing where we were going to be putting the CMT ports. And we also could get an idea of where transitions in rock type happened from this information. So this is the geophysical data, and for example, you can see there's likely a change in rock type where the column on the left changes from yellow to red, and the purple boxes here indicate where we decided to put our 7 ports. So here we are building and installing the CMTs, and you can kind of see from the top it looks like that wagon wheel pasta, and essentially you just cut a little hole all around the outside at the different depths, cover it with a screen, and tighten it in place, and then you just lower the whole thing down the well. And we sampled these CMTs for a number of things to identify whether the groundwater is being impacted by the septic system. So for example, we sampled for artificial sweeteners, anions, field parameters, E. coli, and total coliforms. And in terms of results, the data indicate that groundwater contamination from septic systems is likely occurring. So we can see from the nitrate data that concentrations vary with depth and with time. So in some cases, nitrate levels were higher than 10 milligrams per liter, but went down below our detection limit at other times. But you can also see concentrations follow a fairly consistent pattern with depth. So port 6 near the bottom there is clearly connected to a contaminant source. E. coli is present in 2 of the 3 CMTs, and the pattern corresponds somewhat with the nitrate concentrations, but there's a higher degree of variation with time. And in terms of the artificial sweetener concentrations, there's a higher degree of spatiotemporal variation than nitrate and E. coli. So the other component of the project is the community engagement and Indigenous knowledge side of things. So we've been conducting interviews with community members and elders, and we're incorporating these community perspectives and the Indigenous knowledge that they shared with us into a GIS map. And this map will also contain hydrogeological information, and this will be provided to the Water Committee to make decisions. So there will also be a separate map that is purely just kind of like a story map. So that will include audio clips of stories told by community members and pictures of different places around the reserve that are traditionally and culturally important. And we're going to be using this mapping tool for educational purposes within the community. And we also interviewed members of other First Nations that have worked on source water protection plans, and people from industry, academia, government, and First Nations organizations that are working in this area to identify barriers and opportunities for First Nations source water protection programs. And we've also facilitated a number of community engagement activities, like, for example, bushwalks with elders and youth. There's a pretty big concern in the community that knowledge isn't being passed down. So this is something that has been highlighted as something that's important to the community. We've also done some kids camps. We always have booths at events, and we've done an annual water festival in the community that includes a sunrise ceremony, a big community feast, traditional dancers, a guided water walk on the reserve, a mini boat race for kids up the creek, and then presentations by programs and booths for all of the water-related programs and activities in the community. So it's a pretty big event, and it's a great place to showcase the research that we're doing and really get some community education going. And essentially, community education and engagement has been one of the main focus points for the committee. So this has been, the Water Festival has been a really big part of that. In terms of our upcoming work, so we're going to be doing some groundwater modeling and building on the community perspective that water is life. So it's not just for drinking, it's part of everything that we do. So based on this premise, we're building an integrated source water protection framework in conjunction with the departments of health, education, public works, lands, and fire, to get them to identify how they're already protecting water and how they can work together to incorporate more water protection measures into their existing programs, as opposed to sort of like reinventing the wheel and creating a separate department just for water protection. This is what the community has identified makes more sense for them. And then also community engagement and education piece is also ongoing. So I'd just like to acknowledge the Chippewas and Nawash, our funders, Rezo, and all the colleagues that have supported the project. And that's it for me.
Great, thank you for your presentation. We'll be moving on to our Q&A session now. We have several questions. Were these community or individual supply wells that you were monitoring?
Yeah, so these were kind of like individual wells that used to be used by community members, but are no longer in use.
Oh, gotcha. Did you do any viral testing at all?
No, we didn't.
Okay. Or do you plan on doing it for future? Or is what you have currently sufficient to engage the community in doing something about?
Yeah, I think we're not planning on doing any future viral studies, but definitely from the data that we do have, it is clear that they are in a very vulnerable aquifer zone, and yeah, the groundwater is definitely being impacted. So what we are planning on doing is determining how quickly contaminants are moving from surface or near surface into the well water, or if they're another big concern for the community, because they're actually a fishing community and they're right on the lake, so they're really concerned with how quickly contaminants from septic systems or things that are close to the shoreline are going to move into the lake. So that's kind of the next steps.
Great. And what are some potential management actions being considered based on these results?
Right, so that's something that we're just determining. So right now we are working with the committee to essentially do a risk analysis. So they're going to essentially build up a profile of which risks they deem to be most threatening and which ones they're able to address in the short term. And then in the long term, things that are probably going to be outside of their current funding situation. So they're going to have to be applying for grants to be able to fund some of these measures. So yeah, so there's definitely going to be some short-term things and then long-term considerations. But right now they are interested in looking at, I mean, a lot of their septic systems are very old, and that is one of the main concerns. So they are interested in looking at what other septic technologies are available for more sensitive aquifer areas.
Oh, great. Those were the questions we had for now. Oh, sorry, we have one more. Does anyone other than the tribe have governance responsibility in these areas?
Yeah, it's an interesting question. So, I mean, the relationship with the federal government it's very complicated, but essentially, the federal government was going to be mandatory for First Nations to essentially have source water protection plans a while ago with Bill S11, and that didn't end up going through, and in part because no funding from the federal government was provided to do these plans. And I mean, in Ontario, a lot of source water protection work's been going on since 2006, and millions and millions of dollars have been spent to do that work. So it is definitely a struggle to do it without any funding. So I think that's part of why the federal government hasn't actually made it mandatory for communities to do that work, is that they would probably be on the line for providing some funding for that. But yeah, I mean, there is some shared responsibility with the federal government. It's very convoluted, so that would take a long time to go through it all. But yeah, there is something there.
Great, thank you very much. At this point, we'll move on to our next presenter. Rachel, if you don't mind changing your presenter to Darlene. Darlene, I know you weren't here when we went over logistics, but you should be able to show your screen using the show screen option on your GoToWebinar. Oh, great, you got it.
Hello?
Yeah, we can hear you perfectly fine.
Okay, great. So my name is Darlene. I'm from the University of New Hampshire. And I work with Dr. Robin Collins, and we're trying to enhance E. coli removals from slow rate biofilters, and especially when they're treating low nutrient source waters. Let me see if I can. Okay. So first, give a very quick background on basic elements of slow rate biofilters and their removal mechanisms. And then I'll talk about one of the most common operational concerns of slow rate biofilters, and that's also my problem statement. Now I'll present my research objectives, the methodology used, some of the results and discussion, our conclusions, and our future efforts. So slow rate biofilters, they are one of the earliest forms of water treatment. Their first record use was in 1804 in Scotland. They're very simple in design, construction, and operation. As you can see, there's a bed of sand that's supported by a layer of gravel. And within the layer of gravel, there's the under drains, which the filter water is removed. And on the top of the sand, there's a biological layer which is called the smush stack, and that's where most of the removals happen. A lot of people think that the removals are mainly through physical straining. That's a very popular misconception. A lot of the contaminants that are removed in slow rate biofilters, they are smaller than the pore size. So we know that there are other removal mechanisms too, and chemical and biological, the absorption, and then the contaminants, once they are attached to the media, they can be permanently removed through metabolism from the biofilm. So we know that the active biomass or the biofilm on the slow rate biofilter is very important. But what happens when it's not there, the biofilm is not there, ripening is taking place, for example? If you had to clean the filters, the biofilm is removed, the smush stack is removed from the filters, and then it has to ripen again, and that can take a long time, especially when you're treating nutrient limited source waters. For example, groundwaters, they have very low nutrients, and it can take a very long time for ripening. So we're trying, what we want to do is trying to enhance the biofilters with nutrients. And we know that the major nutrients, the rate limiting nutrients, are carbon, nitrogen, and phosphorus. And we know that also trace minerals, even though they're not requiring large amounts, they're essential for cellular growth. From that, we will try to enhance our biofilters by the addition of nutrients. And since we're adding nutrients to the biofilters, we know that we think that some nutrients, they might favor the growth of specific bacteria communities. And based on that, we'll try to assess the bacteria community diversity after the addition of the selected nutrients. If it's changed, or if it's less diverse or more diverse, or what happens. And another way they were thinking that could work, especially in the beginning of the biofilter operation, is to add small dosages of ferric ion, ferric chloride. And that should help, since ferric chloride acts as a coagulant, that should help to make a more robust biofilm. It speed up the process, and while the biofilter is still ripening, that is expected to help trapping the contaminants, and the bacteria community can metabolize these contaminants. So our first objective was to increase biofilter active biomass. This was the experimental setup. We did this in 3 phases. Phase 2 and 3, they used phase 2 used different carbon, nitrogen, and phosphorus ratios, and the presence or absence of selected minerals. The minerals are all listed in the blue table. And phase 3, it also used all these minerals, but we used different sources of organic substrates. One was powder milk, PM, and the other was glucose glutamic acid. And pretty much the source water was mixed with these nutrients just prior to entering the columns. And one thing that a problem that we had with this experimental setup was that within the nutrient feed solution containers, we noticed some bacteria growth, and these containers are now sterile, so it's not. It's expected to happen since it was a rich nutrient solution. We noticed that there was a problem. So for the next experiments, we changed a little bit the experimental setup, but I'll talk about that later. And the other thing that happened with this experiment was a fungus growth, and that could be because once we seed the columns with a seed from a slow rate biofilter, a local water treatment plant, or from and that developed. We noticed that after a few weeks running, it developed. The fungus developed more than everything else, and the fungus especially, it probably grows faster than the bacteria, and that's why we noticed with using using this specific carbon sources, which are very easy to biodegrade. But the point that I want to make is that by using the nutrients, the columns that were enhanced with nutrients, they showed much higher ATP than the control. The control didn't receive any nutrients, and all the other columns they had within the first 7 days, they had much higher ATP than the control. And you might ask why they vary so much, why some of them go up and some of them go down after 7 days. And there are other things that happen. I won't get into that now, but there are other variables of the process as well. And the fungus contamination was one of them. So we tried to remove or to do other things. And that's why you might see that some of them went up or down. But the point that I want to make is that it did increase the ATP. And then in Jamestown, Colorado, they tried to do the same thing. They had 4 columns, and they enhanced one of them, that was column 3, with glucose glutamic acid. They added 3 milligrams of glucose glutamic acid. And you can see in the gray line that after the nutrient addition, the turbidity removals are much better for the one that was enhanced with the glucose glutamic acid. Column 2 had nitrogen and phosphorus as well, but it was probably organic substrate was probably rate limiting nutrient, and that's why it didn't change. It didn't do any better than the control or the sand column. But one thing that happened with this experiment is that the one that was enhanced with glucose glutamic acid, the head loss increased so much, and then we thought that maybe 3 milligrams per liter is a lot of organic substrate. So some of the conclusions from this objective was that biofilter active biomass is easily increased by the addition of nutrients, especially organic substrates, but this also can favor the growth of specific microbes such as the fungus. And the high dosage of organic substrate, it can also increase the head loss. And then for our next experiments, we did a little bit lower dosage of organic substrate. So we wanted to assess the bacterial community of all the biofilters. And since we had the fungus, we thought that this was probably that's probably what happened. Some of the species grow more than the others. And then we did a DNA analysis, and this is a true 16S. And you can see in the first graph, the bar plot, that the first 2 columns, that was the initial it was the seed. That's why we seed the biofilters with. So it's our initial DNA. It had a much more diverse bacterial community. Each color represents a different, this is done in family level. So each color represents a different family. And then once we, after we run for 3 weeks and we collect samples again, that's what we saw for the other 6 columns. We can see that the orangey, purple, green, and that dark gray, they are very, they were the most abundant bacteria families in our samples. And so we did favor the growth of those specific bacteria. And then if we did a statistical analysis on the sequence variation for richness and evenness, and we can see that they are significantly different from each other. The richness and the evenness of my 6 biofilters, they both decreased after running them for 3 weeks when compared to the initial DNA. So from this run, from the DNA analysis, we did confirm that the select nutrients favor the growth of specific bacteria communities, and that also for the fungus. So those are things that we had to keep in mind, just to be aware if that's something that someone wants to do to enhance the biofilters with nutrients. It might favor the growth of selected specific species. And these so we try to our next objective, that was enhance the biofilter removals by the addition of small dosages of ferric ion, and that's done through the addition of ferric chloride. So this experimental setup was slightly different than the one we did before, and that was because we had the bacteria growth and contamination. So for this one, we used sterile IV bags to hold the nutrient solutions, and we used a UV disinfection light in the source water, and that was to avoid any external contamination. So the nutrients from the IV bags, they are mixed with the source water just prior to entering the columns, and that was done all by gravity. And the nutrients, there was the source water supplement with the same nutrients that I showed before. There was they're listed here again. And today I'll just talk about columns 1, 2, and 3, because columns 4, 5, and 6, they are still running, and I won't talk about the results from those yet. This is just a picture of the experimental setup. So you can see the IV bags with the nutrient feed solutions on the top, the source water. You can see the UV light for the disinfection. And the flow rate from the IV bags, they are controlled by these IV flow rate controllers. So here's the first graph is for the ATP. So we want to see if the ATP is correlated also to the addition of ferric chloride. And it shows that with the addition of ferric chloride, it has higher ATP levels, but 0.2 or 0.5, they're not that different. They're higher than the control, but not that different from each other. We achieved a lot higher ATP concentrations when using organic carbon as well. But it does show that it helps with the ATP, and that might be because it acts as the coagulant and might trap more contaminants, more nutrients in the water, and it helps with the bacteria growth. And then we wanted to challenge that with the E. coli to see how that performs. And the ones with higher iron had better removals in 3 weeks of running, and then we kept those, and then with the same concentration of iron, and after 5 weeks we saw they still kept the same trend. The control increased a little bit, but not as much as the ferric chloride columns. And this is the correlation between ATP and E. coli removals, and also for iron intake and E. coli removals. So the higher the iron intake, the higher the removals, and the higher the ATP, the higher the E. coli removals as well. Here's just a picture. This was a 3 weeks run time, and you can see that the control in the top, you don't see any biofilm. You don't see anything there. But then if you look at column 2, you see this orangey color, and you can see that it's starting to form some kind of biofilm. And then column 3, you can see a lot more this reddish color on top, and that's the coagulation, the iron coagulation there. So with the conclusion from this run is that the addition of low dosage of ferric iron did develop a more robust smudge stack and also enhanced the E. coli removals. In our future efforts now there are to finish our current run, which were the one that we're assessing the impact of combining iron and carbon, and also using different carbon sources. There was the powder milk and glucose glutamic acid on biofilter performance, and keep assessing through DNA analysis if whether or not a more diverse bacteria community or even a specific bacteria species, they are better for removals. Because it could be that you expect that the more diverse the bacteria community, the better the removals, the healthier the bacteria community is. But it might be that there's a specific type of bacteria that is also very good for removals, and if we can grow that bacteria by the addition of selected nutrients, that'll be great. These are my references, and I'm now open for questions.
Thank you, Darlene. For one question, in your research, were you able to identify the specific species of bacteria that selectively grew off feeding off nutrients? Like when you were showing us the bar or the chart, which had like the bacteria growth by date, it was like the green and orange bar.
I have the name for all of them. I didn't bring because they're pretty long, but I know what they are, and some of them I can identify the species, but a lot of them the species is unknown. So I knew the family, but I didn't know the species. But for all this, the ones that are dominant in my biofilters, I could tell. And what happened, I had a lot of iron in that run as well, and there was ferrous iron. So there is oxidizing iron bacteria, and I don't remember the name of the bacteria right now, but if you want, I can send to you later which species are dominant.
Great. Those are the questions we have for now. So at this point, I would like to conclude our webinar session. Again, this will be posted as a video on the Drinking Water Center's website. So I would like to thank our 3 presenters today once again, and I hope everyone has a great day. Thank you.